Thank you all for joining us today at our Climate Change Speaker Series, part of our Earth Day Half Birthday Week of Actions. I want to thank our sponsors, Centene, Subaru, Missouri American Water, the City of St. Louis, Metro Lighting, MSD Project Clear, the Solid Waste Management District of St. Louis, Jefferson County, Missouri DNR, and Great Rivers Greenway. Without their generous support, we could not put together this Earth Day Half Birthday Week of Action. If you missed it, Thursday was a very successful green curbside hop in the Green Dining District of Maplewood, celebrating our Green Dining Alliance certified restaurants. And we organized 3 neighborhood cleanups this weekend, sponsored by Subaru. They were in St. Louis, South City and Dutchtown, up in North County of St. Louis and Pine Lawn, and in the Webster Groves Deer Creek Park. So climate change is not only impacting our environment, but it impacts our lives, creating stress and trauma that can debilitate our ability to be creative and empowered to connect with our community and affect change. And we have 4 amazing speakers today, each sharing a different perspective around climate change, from Reverend Lauren Buck, whom we just heard, addressing personal trauma, gender oppression, and our need for connecting ourselves to the environment. Right now is Zeke Hausfather, climate model expert, looking at what is climate change and what we can do about it. Followed by David Lubbig and Myra Jackson, focusing on our Mississippi River that covers a 34-state watershed. And finally, how to activate into action with the inspiration and wisdom of Marlo Baines, youth director with Earth Guardians. I hope you can stay with us to hear all the segments, but if not, all segments will be recorded and on our website at earthday-365.org. If you have any questions for our speakers, we'll be monitoring the Zoom chat and Facebook Live feeds and make sure that we can get those to them. Zeke Hausfather is a climate scientist and energy systems analyst whose research focuses on observational temperature records, climate models, and mitigation technologies. He spent 10 years working as a data scientist and entrepreneur in the clean tech sector, where he was the lead data scientist at Essus, the chief scientist at C3.ai, and the co-founder and chief scientist of Efficiency 2.0. He also worked as a research scientist with Berkeley Earth, was a senior climate analyst at Project Drawdown, which created this compendium, and the US analyst for Carbon Brief. He has master's degrees in environmental science from Yale University and someplace in Amsterdam. I wasn't quite sure how to pronounce that. And they're in climate science from the University of California, Berkeley. Please welcome Zeke Hausfather.
Oh, thanks, it's great to be here. So let me share my screen really quick and get this working. And turn that to present mode, maybe. There we go. Okay, can you see my screen okay?
Yep, everything looks good.
Perfect. Okay, so to dive right in, I'm gonna talk a bit about the science underlying climate change. So how the climate has changed, why we know that it's due to human activities, how we model it and how well our models have done. And then talk a bit about what might happen in the future. And what are the major factors that really determine how much the climate will change in the future, and what can we do about that? And so to dive right in, this is probably one of the more iconic graphs of climate change. This is showing global temperatures since the year 1880. This is from NASA, though there's a bunch of different groups, including my own group, Berkeley Earth, that produce similar records to this. And essentially what we see is that the world as a whole has warmed about 2 degrees Fahrenheit, or about 1.2 degrees centigrade, since the year 1880, with most of that warming happening in the last 50 years. It's really since 1970, we've seen an acceleration of warming. And when we talk about global warming, we're really obscuring a lot of the detail in this single number, this global average, because it turns out that some parts of the world are warming much faster than others. The land on average is warming about half again as fast as the globe as a whole, in part because the land warms a lot faster than the oceans. The oceans can take up a lot of heat. They warm more slowly. Some of the heat the oceans take up goes down into the deep ocean, whereas the land warms up very quickly. And so, when we talk about 2 degrees warming, 2 degrees Fahrenheit warming since 1880 globally, we're really talking about 3 degrees Fahrenheit warming over land. And then there's some regions of the world, like the Arctic, that have warmed much faster than that. So in the Arctic, we've seen regions of 4, 5, even 6 degrees Fahrenheit warming over the last 50 or 60 years. And we expect that sort of pattern to continue as the world warms. The land will continue to warm faster than the oceans. The Arctic will continue to warm faster, and the high latitude areas in general will continue to warm faster than the world as a whole. And there we go. So the other thing that we know, besides the fact that the world is warming, is that human activity is driving effectively all of the warming we're seeing. We don't have much evidence that there's other factors like the sun or volcanoes or changes in the Earth's orbit that are responsible for the warming we've seen. And let me show you a quick video that I put together that sort of tries to illustrate this, and hopefully it'll play okay, because video over Zoom is sometimes better than others, but let's see if this works. And can you guys hear the audio, or is it just on my end? Because I can talk over.
I'm not hearing that.
You're not hearing the audio? Okay. So let me back up for a second and just talk over it then. So essentially, what's causing global warming? Here's the observed temperatures in black that I showed earlier. Every dot is a different year. And we know it's not the sun, simply because we have satellites pointing at the sun. We know that its output hasn't changed much. It's not volcanoes. Volcanoes call cooling. They cool the Earth for a year or two when they erupt. It's not aerosols. These are tiny particles that reduce warming and reflect more energy back to space. So our aerosols have actually cooled the Earth a little bit. Similarly, land use has cooled the Earth a bit, in large part from conversion of dark forest to paler pasture. It's not ozone pollution, which has warmed the Earth a little bit in the lower atmosphere, but it hasn't been a huge factor. It's really greenhouse gases. Rising concentrations of greenhouse gases as a result of human activity are by far the biggest cause of the warming we've observed. And when we combine all these, when we compare the human factors and the natural factors, it's clear who's responsible for global warming. In fact, here's sort of highlighting that graph I showed at the end of that video, and hopefully the video came through okay. But if we just look at natural factors, things like solar activity, volcanic events, et cetera, if the world were just experiencing those and we didn't have our greenhouse gas emissions, the world would have actually cooled very modestly over the last 150 years. So effectively all, and actually slightly more than all of the warming we've observed is due to human activity, because these natural factors are offsetting a little bit of that warming. And this is not just my conclusion. This is a conclusion that has been reached by the Intergovernmental Panel on Climate Change. It's a conclusion that the recent US Fourth National Climate Assessment that was published by the Trump administration and signed off by 13 different executive agencies also said. He said more than 100% of the warming we've observed is due to human activity. And so this is not really controversial at all in the scientific space, even if there might be some political controversy about it. And then we have climate models that we've been building for really the last 50 years. The first climate model came out in 1967. And scientists have been improving them and refining them ever since. And these climate models have done a remarkably good job in both projecting the warming we've seen and explaining the past warming we've seen. And so, what this graph is showing is a bunch of different surface temperature records, so global temperature records in colored lines from 6 different groups: NASA, the Hadley Center in the UK, NOAA, my group, Berkeley Earth, Coughton and Way, Copernicus, which is the European Union research group. And then the black line is the average of all the climate models that were included in the last big international assessment by the Intergovernmental Panel on Climate Change. And the gray area is the range of all the models that they looked at. So the black is the average of all the models, the gray is the range. And generally what we see is that models have done a really good job of predicting both the warming we've seen and the past warming. Now, since these models came out in 2013, they're really only trying to there's only about 7 years after they were published where we can compare what they said would happen and what actually happened. And all of the past is sort of essentially running those models backwards, taking the same level of CO2 that, was in the atmosphere in the real world and putting that into the model and seeing what the model says would happen. But we can also look at older climate models. As I said, we started publishing climate models in the 1970s or late 1960s. And so we can look at those models and say, what did those models say would happen after they were published? Because clearly, they can't know what was going to happen in the future. And that's a really good test of the skill of our science to predict how the Earth's climate is going to change. And so this video shows a few examples of some past models and how well they did. So there's the actual temperatures from those different groups. Let's compare it to climate models. This is a 1975 model by Wally Broker. There's a 1981 model by James Hansen at NASA. There's another 1988 model by Hansen. There's the first IPCC report. There's the second IPCC report. There's the third IPCC report, the fourth IPCC report, and then the most recent, the fifth IPCC report. And as you can see, all of those dark lines overlap quite well with the observed temperature record. Our models have had a really good history of predicting what would happen accurately into the future. And so, we have these models that we can run into the future to look at how the climate would change. But when we're trying to do that, we're really dealing with three different sets of uncertainties. So to figure out if the world is going to warm by, 4 degrees Fahrenheit or 8 degrees Fahrenheit by the end of the century really comes down to these three fundamental uncertainties in the climate system. The first is future emissions. How much CO2 and other greenhouse gases will humans put up into the atmosphere? The second is climate sensitivity. And what we mean by climate sensitivity is effectively how sensitive the climate is to atmospheric greenhouse gases, how much the Earth will warm, for example, if we double the amount of CO2 in the atmosphere. And the reason why climate sensitivity is fairly uncertain is because it depends on a lot of what we call feedbacks in the climate system. So essentially, once you increase CO2 in the atmosphere, it causes a lot of other things to happen. So for example, if you increase CO2, it warms the Earth, it causes ice to melt. Now, ice is very reflective, it's very bright. Most of the sunlight that hits ice bounces back up to space. That's why you get blinded, if you get out at a door at noon in like a snowy field. And if you melt that ice and you melt that snow, suddenly you're replacing this very bright reflective surface with a darker surface, with trees, with vegetation that absorb a lot of the sun's energy. And what that means is when you absorb more of the sun's energy, you end up warming the environment around. And so as the world warms, more snow and ice melts, more darker surfaces are revealed, more sunlight is absorbed by the Earth's surface, the Earth warms more. So that's a feedback, what we call positive feedback. There's other ones like, the more the Earth warms, the more evaporation you have over the oceans and lakes and rivers, the more water vapor goes up into the atmosphere, the more water vapor can be held in the atmosphere before it rains out, because the warmer the air is, the more moisture it can hold. And water vapor itself is a greenhouse gas. It also traps the sun's heat, just like CO2 does. And so as the world warms, you get more water vapor in the atmosphere, and that is another positive feedback. It means the world warms more than it otherwise would have because there's more water vapor. There's also some negative feedbacks that sort of press back against that. The warmer the Earth gets, the more energy it releases back to space. That's kind of the most basic one, which prevents the Earth's climate from running away, which is a good thing. But because all of these processes are really complex and we don't have a great handle on them and don't have a great understanding of all of them, we end up with this range of estimates of how sensitive the climate is to CO2, even if we know what future emissions would be. So it's a separate type of uncertainty. And then finally, the third type of uncertainty is what we call carbon cycle feedbacks. And what carbon cycle feedbacks are essentially is how much of our emissions stay in the atmosphere versus get absorbed by the land and the oceans. And today, about half of what we emit ends up staying in the atmosphere for the long term, and half of what we emit is absorbed by the oceans and vegetation. And that's a good thing. It means that essentially climate change is happening half as slowly as it would if all of our emissions stayed in the atmosphere. But what we do know is that the ability of the Earth to absorb our extra carbon dioxide emissions is going to change as the Earth warms. Warmer ocean waters are less able to take CO2 out of the atmosphere, in part because they're also more acidic when they're absorbing a lot of CO2, and that affects, there's complex chemistry reasons, but the warmer and more acidic ocean waters are, the less able they are to take up extra CO2 in the atmosphere. And similarly, over the land, you have different factors at work. On one hand, the more CO2 you have in the atmosphere, the more growth you'll have of certain type of plants. Like there's a reason we pumped high levels of CO2 into greenhouses to get more growth. And so that'll take up some extra CO2 because you have higher plant growth. At the same time, if you have higher temperatures, you could have more wildfires that release more carbon dioxide to the atmosphere. You could have drier soils that kill crops and trees and plants. You could have things like pine bark beetles that are killing a lot of the trees out here in the West expand their range because they can survive during the winter because it's warmer and it doesn't kill them off anymore. And so it's really hard to figure out exactly how all these different factors will combine to affect how the Earth can absorb our carbon dioxide emissions. And so these three sets of uncertainties really determine how much warming we expect to happen by the end of the century. And so I'll walk through each of them and talk a little bit about what we think might happen and what our climate models think might happen. And so I'll start with emission scenarios. And in many ways, this is the single most important thing. And it's also the only one we can actually control. We can choose how much global emissions we want to have of CO2 and other greenhouse gases. And so what this graph shows is the latest set of emission scenarios that have been developed in the run-up to the next Intergovernmental Panel on Climate Change report that's going to come out next year in 2021. And the black line is historical emissions. So every year since 1980, the globe has emitted a certain amount of greenhouse gases. Back in 1980, we're emitting about 24 gigatons or 24 billion tons of CO2. Today, we're emitting about 40 billion tons of CO2. So emissions have increased about 40% just in the last 40 years. And the question is, where are we going to go from there? Are we going to go toward a world where they triple by the end of the century and we have about 5 degrees warming? A world that is dominated by coal, where we're still building tons of coal plants all around the world, and it's the fuel that powers most of society for the next century? Or are we going to end up in a world where we rapidly cut our emissions and limit warming to below 2 degrees? And that's a world where we stop burning fossil fuels fairly quickly. We replace them with things like solar panels, wind turbines, enhanced geothermal, advanced nuclear, carbon capture and storage, electric vehicles. And there's a whole slew of different technologies that can play an important role in helping us move towards some of these low emissions world. Or do we sort of muddle through? Do we end up in a world where we don't increase our emissions dramatically, but we also can't really get our act together enough to reduce them dramatically? And that sort of muddling through ends up in a world of about 3 degrees warming. And I'll talk a little bit about this later, but it turns out that we're probably on the muddling through track right now. But at the same time, if we have the political will, if we can get people to take action, if we can get policymakers to take action, it's certainly possible to bend the curve of emissions down toward a world of below 2 degrees warming, 2 degrees centigrade, which is the sort of target that's been adopted by the international community in the context of the Paris Agreement on climate change. So emissions are one side, but those emissions then have to turn into concentrations of CO2 in the atmosphere. And as I mentioned earlier, not all of our emissions stay in the atmosphere. And so there's a fair amount of uncertainty about how much remain in the atmosphere. And so here are 4 basic concentration scenarios that were used in the last generation of climate models, the so-called RCPs, which are a little technical, but if you follow climate stuff, you probably have heard of them, at least in passing. And so, there's a world where concentrations stay around today's levels of 400 parts per million by the end of the century, which is a world of around 2 degrees warming. There's a world where emissions increase a bit to about, or concentrations increase a bit to about 550 parts per million from about 400 today. 412, I think, is the latest. And that's a world of about, 2.7 degrees warming. There's a world where they continue to increase to about 600, 650 parts per million. That's a world of a bit above 3 degrees warming. And then there's a world where we, burn all our coal and we have 900, 1,000 parts per million of CO2 by the end of the century. And we have really catastrophic levels of warming of 4 to 5 degrees. Now, as I mentioned, there's a lot of uncertainties in exactly how our emissions translate into concentrations. And so if you look at this figure here, the end point is the year 2100. And so in this next figure, the same values are these black bars for the 4 scenarios. RCP 2.6, the 2100 value is this big black bar. For RCP 4.5, it's that big black bar, et cetera, et cetera. But that black bar is a single best estimate. In reality, there's big uncertainties around how the ocean and how the land's ability to uptake or to take up our emissions will change. And so what this chart is showing is 2 different sets of modeling efforts that scientists have done to better quantify how big an uncertainty there is around that best estimate, around that black bar. And so here, the black bar is the best estimate, and every dot is a different climate model that estimates how much CO2 concentrations could actually be in the year 2100, accounting for all these uncertainties and the ability of the land and the ocean to take up our extra CO2. And so there we see, even though in the very high end scenario, our best estimate is around 900, 950 parts per million of CO2 by 2100, it could really be anywhere between 800 or 1600, a really high number, if the ability of the land and the ocean to take up our extra CO2 decreases more than we expect. And we have a hard time narrowing this uncertainty because it's such a complex system. And so this should be a bit worrying to us, right? Because if we're planning on ending up here and we end up here, that's a much worse outcome than we thought was going to happen. When it comes to climate change, uncertainty is really not our friend, and we need to remember that. And the fact that there is so much uncertainty in our ability to perfectly model the climate means we should be more cautious, not less, because we really can't rule out some of these low probability, really high impact, worst case outcomes. And then we have to go from concentrations to warming. And so that itself has its own set of uncertainties, the climate sensitivity I was talking about earlier. And so what this plot shows is all of the climate models, the individual climate models in the last big Intergovernmental Panel on Climate Change report. Now every different climate model is an individual line, and they're colored based on what emission scenario they use. So what concentration scenario they use, the 4 concentration scenarios I discussed earlier, the RCPs. And so even within, say, an RCP 2.6 scenario, which remember is a scenario developed to limit warming below 2 degrees, there's some models that are above 2 degrees. There's some models that are down to 1 degree warming, cooler than we are today. And so there ends up being a huge range of uncertainty because of this climate sensitivity. And that uncertainty increases the higher concentrations you have. And again, it's a similar argument that uncertainty here shouldn't be our friend, right? Even if we're hoping to limit warming below 2 degrees, there's still a chance it might be above 2 degrees. And so that means, we should try to cut emissions as much as possible to avoid some of these really high-end, high sensitivity, high carbon cycle feedback outcomes. I'll talk about this briefly because it's a fairly complicated plot, but this is essentially trying to do the same thing I showed you earlier for the uncertainty and carbon cycle feedback. So the standard climate models that are used by the Intergovernmental Panel on Climate Change don't include any uncertainty around carbon cycle feedbacks. They just use a single best estimate. And so the first bar, well, the colors are the 4 RCPs I discussed earlier. So RCP 2.6, 4.5, 6.0, 8.5. It's the same color scheme that I had in that last plot. And what I'm showing here is the first bar is the standard climate models that everyone uses in terms of how much warming you're going to have in the future. The second bar and third bar are for these 2 different experiments that have been done to look at the uncertainty and carbon cycle feedbacks, essentially saying, given the uncertainty in what concentrations will actually be by the end of the century for a particular emissions pathway, what's the range of warming that could actually happen? And so the general point is that when you include carbon cycle feedbacks, you get a lot more uncertainty in how much the Earth will warm, both an increase in the high end of warming and a more modest decrease in the low end of warming if carbon cycle feedbacks are higher than we thought. And so, what this says to me essentially is, if we're on track for, say, a modest mitigation scenario, like an RCP 4.5, our best estimate is the world might warm by a bit under 3 degrees by the end of the century. But there's a big uncertainty around that. Just looking at climate sensitivity, it could be anywhere between 1.6 and 3.3. But when we include carbon cycle feedbacks as well, it could be anywhere between 1.5 and 4 degrees centigrade. And so, even a world that we think is on track for, 2.7 degrees centigrade warming, we could end up with 4 if we're unlucky. And so we really need to take that into account. And so I've talked a lot about different emission scenarios and different concentration scenarios. And, obviously a world where we triple our emissions by the end of the century and a world where we get to 0 emissions by 2050 are very different worlds. And can we say anything about which of those worlds are more likely based on where we are today? And I argue that we can. And so what this plot shows is all of the old projections of future emissions. So starting in 1990, and then another set in the year 2000, then another set around 2010, or the late 2000s, the world has had various different efforts to try to predict what future emissions might look like. And it turns out today that, at least from the standpoint of fossil fuel emissions, which are in some ways the most important ones because they are most of our future emissions, we're somewhere right in the middle. We're not on the worst case scenarios. We're certainly not on the best case scenarios of limiting warming to below 2 degrees. We're sort of in the middle of the range of future scenarios. And so what I say is, while current emissions are inconsistent with limiting warming to well below 2 degrees, we can't say with any confidence that they make, a particular default or business as usual outcome more likely or not. We're not necessarily on the highest emission pathway, which is a good thing. And we can also say a little bit about where we are today based on the policies that countries have adopted, because a lot of our past emission scenarios looked at worlds where nothing was done on climate change, where everyone just kind of kept going about business as usual, emitting like climate change didn't exist, and like there was really no worry about the Earth's future. And we certainly haven't taken climate change as seriously as we should as a society. We also haven't been completely cavalier. We have enacted a fair amount of policies. We have invested a lot in clean energy technologies. We have started moving the world away from coal. And so the world that we're on right now is sort of this world of muddling through. We're no longer really on track for some of these worst case 5-degree outcomes, 5-degree warming outcomes or 4-degree warming outcomes. We're also certainly not on track for outcomes that limit warming below 2 degrees. We're sort of in a world that's moving toward about 3 degrees warming today with, again, a big uncertainty because of these uncertainties in climate sensitivity and carbon cycle feedbacks I talked about earlier. And that is limited good news in a way. Another way to look at it, there was just a big international energy report that came out last week called the World Energy Outlook by the International Energy Agency. And what they argued is essentially the green line here, that global emissions are going to be flat for the next 20 years. That, it may well be that global emissions peaked back in 2019, and in part due to the COVID crisis and a slowdown in global economic growth associated with that, but also due to the rapid, acceleration of deployment of clean energy. We're probably not going to get back to 2019 levels of emissions in the future. We might, it's hard to predict. But there's a good case to be made that global emissions might have peaked last year. That's great news. It's a world where global emissions have already peaked is much better than a world where global emissions are continuing to increase. The problem is that climate change is a cumulative problem, not a sort of flow problem. And what I mean by that is that our carbon dioxide emissions accumulate in the atmosphere. Last year's emissions are still up there. Most of them, the year before that, are still up there. Most of them, a typical molecule of CO2 we put into the atmosphere lasts about 100 years on average with a very long tail. And so what that means is even if emissions are flat, the world will continue to warm because carbon dioxide will continue to accumulate in the atmosphere. In fact, if emissions are flat, the world will pretty much keep warming at the rate it's been warming for the last few decades. If they accelerate, it'll warm faster. If they drop, it'll warm slower. But the world will continue to warm until we get our emissions all the way to zero. The only way to stop global warming is to get emissions to zero. And so, peaking emissions is a first step, and it's a good step. But it's a first step on a very long journey down to get all the way to zero emissions. And at least with the current policies enacted today, we are not remotely on track for that. And so while we've bent the curve down, to borrow some language from our current pandemic crisis, we need to still bend it down much further going forward. But I'd also argue that a world of flat emissions is one where it's much easier to bend down the curve to zero than a world of continuing increase in emissions. And so we have some things to be thankful for. We have, rapidly falling prices of clean energy that are, in many ways falling faster than we thought was possible 5 years ago. Things like battery storage and solar panels are getting ridiculously cheap and are the cheapest. Solar in particular is the cheapest new form of energy in many parts of the world. And coal, which there was a lot of worry that it would be the dominant fuel of the 21st century, peaked back in 2013. Global coal use has been lower every year since. And, we have good reason to think now, and the IEA, the International Energy Agency, in the report last week projected that, coal is going to go into structural decline around the world going forward. It's going to keep dropping. We're not going to see a resurgence in coal. And it's been interesting that, here in the US, we've really made remarkable progress in closing down coal. Coal used to be more than half of all of our electricity generation. Today, it's less than a quarter. And we're, expecting to see really dramatic declines in coal in 2020. In fact, despite the Trump administration coming into power, arguing that they're going to end Obama's war on coal, what we've actually seen is the exact opposite. Coal plants have closed faster during Trump's presidency than they closed during Obama's presidency. not because Trump was trying to close them down. In fact, his administration did everything possible to save them. They rolled back every environmental regulation they could find that would limit coal in any way. But the problem is, even without environmental regulations, coal is simply more expensive than renewable energy and natural gas in the US today. And so by making clean energy cheap, we've really managed to make a big dent in our emissions in a way that is insulated from the policy process. You know, the one challenge of having strong climate policy, which we want, but it's also potentially, you know, at risk of being repealed every time a different administration comes into power. You know, a world where the US oscillates between having really strong climate policies and having no climate policies every 8 years or so is one that where it's a lot harder to tackle climate change. And so if we can make the carbon-free technologies, things like electric vehicles, solar panels, wind turbines, as cheap and as effective as the things that they're replacing, then we don't necessarily need as big a lift from policy, though we still need a big lift from policy. And so that's what makes me hopeful. So that's about it. Some important takeaways before I end is, you know, I've been talking a lot about the current policy world that the world is on, this sort of muddling through to 3 degrees, but current policies are neither a ceiling or a floor on future emissions. You know, there's certainly a world we can envision where the sort of rise of populism we've seen in the last few years in places like the US, Brazil, the UK, Australia, continues to be the norm, where more governments come into place dedicated to repeal existing policies, maybe where administrations start to actively subsidize people to burn coal. You know, it's not likely, but it's possible, right? So we certainly need to worry about that. We shouldn't become complacent that a current policy world is necessarily a ceiling on our emissions. But also there are worlds where, you know, technology continues to advance faster than we anticipated. And where even in the absence of effective new policies, we still end up in a lower emissions future than we thought. You know, probably not getting to 2 degrees or even 2.5 degrees without strong policy, but certainly could be a bit lower. You know, from an emissions standpoint, as I mentioned, it's hard to justify some of these very high-end scenarios of emissions tripling by the end of the century, but it's still quite possible for a lower emission scenario to result in higher levels of warming because of these big uncertainties in climate sensitivity and carbon cycle feedbacks. And so that these big uncertainties in how the Earth responds to our emissions, I mean, we really should try to address the one climate factor we can, how much we actually emit. And, you know, here's just to close on the latest climate action tracker, which is a group that, you know, does a lot to track all the different things countries around the world are doing to combat climate change. And their latest update from last month is they now expect, you know, the current policies that countries have adopted to put us on track for about 2.9 degrees C warming by the end of the century, you know, with a range of 2.1 to 3.9, and pledges and targets to put us around 2.7. The difference between those two is pledges and targets are things that countries have committed to do, but are not yet reflected in actual laws enacted by countries. And there's an important caveat to this graph is this doesn't include China's new pledge to get to net zero emissions by 2060. Which is really huge. Like China is the biggest emitter in the world by, you know, a factor of 2, bigger than any other country. And so if they're really serious about cutting their emissions all the way to zero in the next 40 years, that would make a huge dent in future emissions. And so if you included that, pledges and targets would be about 2.3, 2.4 degrees C by 2100. Again, still not below 2 degrees, but getting a lot closer than, to be honest, a lot of us thought was likely to happen. And so, you know, the world is starting to move seriously on this. You know, the energy transition is real, and 2020 has shown us that. And, you know, we just need to keep bending that emissions curve downward and get to below 2 degrees and hopefully below 1.5 degrees, though that's a heavy lift. So that's all I had, and happy to answer questions that folks might have.
Zeke, this is fantastic. I was hoping that as you're talking about emissions, let's bring that personally, and if folks were willing to put into their chat, like just ideas about how they're reducing their emissions in their daily lives. And that could be, you know, working on policy changes. It could be, you know, like doing solar panels on their house. So feel free to bring your personal action steps into the chat so that folks can join in on that. If you have any other questions, I guess that's kind of really cool news about coal, you know, maybe peaking way back then, maybe global emissions achieving a peak in 2019. Are you worried at all about this post-COVID as a real strong boomerang, rubber band, and emissions really moving higher after the shutdowns?
It's certainly a worry. You know, a lot of it depends on how countries prioritize recovery efforts. You know, if they're spending all their money supporting their coal industries and their steel industries and their concrete industries, then and use that as the engine for future growth, then it certainly could drive emissions back up. You know, if instead countries are investing in things like modernizing their grid and building more renewable energy and green jobs, and in things that aren't as directly tied to emissions, then it could actually be a boon. In fact, you know, a number of countries like the European Union, for example, have really prioritized green recoveries in the period after COVID. And hopefully China will too. That's sort of the big question mark right now is what's going to happen in China. You know, are they going to take this new target they announced and actually translate it into meaningful policy in the short term in terms of their recovery? Or is it going to just kind of be this like, we're going to do this in 40 years and, you know, kind of work out the details later, because that'll make a big difference in emissions in the next few years. You know, the US too, obviously, though, we are, you know, half of China's emissions. So they tend to dominate at least the global picture on these sort of things. And there is a real chance that the US will, you know, take some serious action on this if there is a new administration in a few weeks, or a new administration in the beginning of next year. And so, you know, I'm certainly hopeful that we can use COVID and the recovery from COVID as an opportunity to move the world in the right direction instead of in the wrong direction.
Yeah. Well, thank you so much, Zeke, for bringing all this wonderful data to bear, trying to bring it to our mainstream audience in an understandable way. I love seeing, you know, the charts of historical stuff, and then seeing all the different lines going up and down, and kind of giving, kind of pulling back the curtain a little bit about what it is that you're doing. And yes, the sense of complexity that you are trying to manage is huge, shall we say.
It's a little unfortunate. You know, we scientists like to run experiments, and if we had like another planet sitting next to the Earth that we could change the atmosphere on and see what happened, it would be great.
A little control experiment.
Yeah, and unfortunately we don't. So we have to build planets in our computers, in our computer models. And you know, we've come a long way in the last 50 years in terms of doing that, but the Earth is incredibly complicated and it's really hard to get everything perfect. And so we also want to be humble that, you know, to borrow the one good thing Donald Rumsfeld ever said, there are unknown unknowns out there that we really need to bear in mind, because, you know, we've never done anything quite like this, at least in the modern history of our planet. And so knowing exactly how the planet will respond is you know, a challenge. Yes, there's no planet B, as Laura pointed out in chat.
Exactly.
I think Dan J had a question in chat as well. He said, you know, we know about West Coast fires and Gulf hurricanes. Looking internationally, what are other areas that are already being affected? So there's certainly a lot of different climate impacts all around the world. And, you know, we tend to focus on certain ones in the US because they affect us the most. But some of the other big impacts we've seen around the world is, you know, coral reefs have been devastated in recent years by bleaching events. So corals are very sensitive to ocean temperatures. They've evolved to live in waters that only vary by a couple degrees between winter and summer. And so what's happened in recent years is as those oceans have warmed, it's pushed the corals out of the range that they evolved to live in. And when that happens, the corals expel their symbiotic algae called zooxanthellae and bleach. They turn bone white and die. And, you know, if that happens once, and then there's like 5 or 6 years of normal temperatures, the coral can recolonize, it can recover, it can come back. But the problem is, you know, it's in 10 years, 12 years ago, it was like, you know, it happened once and then there'd be a long period of time and it would happen again. But now those oceans have warmed so much that these bleaching events are happening almost every single year. And, you know, it's very difficult for coral to recover from that. And so, you know, much of the world's coral will probably be lost in the next 20 years in the absence of very rapid climate mitigation. So that's a very, very clear impact. Another that we see, you know, very dramatically is loss of Arctic sea ice and loss of snow in many high latitude regions. You know, we've lost about half of the sea ice in the Arctic, a bit more than half, since 1970. And we're expecting to have the first ice-free year in the Arctic, probably by around 2050 or so, if we sort of continue in our current track. Could happen a little before, could happen a little after. It depends a lot on how big the storms are that particular year, or these other factors that can influence the formation of Arctic sea ice. But there's a very clear decline in Arctic sea ice. And there's growing evidence that that decline can affect weather patterns in different regions around the world. Another aspect, or another thing we've seen from climate change that's very clear is increased flooding. We've seen some of that in the US and the Midwest, but as I mentioned earlier, one of the biggest sort of feedbacks from climate change is that warmer air can hold more moisture. And so as the air warms, as more moisture ends up in the atmosphere, when big storms happen, when big rainy events happen, they tend to be much more intense. And so, we've seen a very clear signal around the world of heavy rain getting more intense. And more intense heavy rain can lead to more flooding, more mudslides, more sort of dams bursting from overcapacity. Another thing we've seen from climate change that's also a very robust signal, both in observational data and in our climate models, is that while heavy rainfall is becoming more intense, in many regions of the world, rainfall is also becoming more sporadic. So you often have fewer but more intense rain events. And that can be a challenge for things like, dams, where you're planning for more regular rainfall and not, these sort of discrete heavy events. We've also seen a very large decline in mountain glaciers all over the world. Almost every glacier in the world has been in decline, and many of them very, very rapidly. And that obviously affects a lot of rivers that folks rely on for agriculture, because many of the world's great rivers are fed by mountain glaciers. And so, as they melt rapidly, that leads to more water in the short term, but it also is going to mean a lot less water in the longer term as these glaciers dramatically shrink. And then a big issue that's been affecting people all around the world, of course, is sea level rise. The oceans have risen, a fair bit in the last century, and we expect them to rise anywhere between 1 and 3 feet, most likely by the end of the century. And many regions of the world, places like Bangladesh that are very low-lying, have started to see more and more extreme flooding events. And certainly by the end of the century, much of those countries could be inundated. Small island nations have a lot to worry about for that. If your entire country is 5 feet or so or less above sea level, a 3-foot sea level rise could wipe out most of your country. And there are some ways to adapt to that. The Netherlands is entirely below sea level, or almost entirely below sea level, and has managed through massive dikes and other huge public works. And so, this kind of comes to one of the big equity challenges of climate change, is that, I'm not as worried about people in the US and in Europe responding to climate change as people in, say, Bangladesh, right? Because we can build giant seawalls, we can build air conditioners, we can even go as far as Dubai and put like air conditioning vents in our sidewalks so people can walk around. It's not a good idea, but if we really wanted to, we have the resources to adapt to some of these changes, in part because we're wealthy as a society. But a lot of the world isn't. And it turns out that the countries that are most impacted by climate change, that have the least ability to adapt to the changes we expect to see, are also the ones with the lowest emissions, because the two go hand in hand, right? Rich countries have higher emissions than poor countries. And so the people who suffer the most from climate change are the people who are the least responsible for it, which is really, a challenge around equity, right? We're essentially saddling the poorest people in the world with the biggest impacts of our activities.
And that also happens right here in our country. I don't want people to lose fact of the fact that we have people being displaced from their homes right now because of sea level rise, like in Miami and other seacoast cities, that all the affluent people bought beachfront property, and now they want to get into the city, which has the only rock and in the area. And so the gentrification that's happening in urban settings is displacing more Black people and people of color.
That's a really good point. When I said equity, I should have emphasized that it's true both between countries and within countries. There are many communities, poorer communities, that are primarily communities of color in the US, that are very high risk from climate change and have a lot less resources to adapt to the changes that we expect to see than some of the richer communities. And so, it happens both between countries and within countries.
Yeah. Well, thank you so much, Zeke, for this fantastic overview about climate and all this great stuff. We know that there's still more work to be done. Really appreciate and grateful that you took the time of your schedule to be with Earth Day 365 here in St. Louis, Missouri.
It's great to be on.
Yeah. And so for the rest of you, I hope to see you at 3 o'clock for David Lubbock and Myra Jackson. Thanks to a partnership with the Missouri Historical Society, we're able to present this segment of their Our Rivers conversation honoring the great rivers. And thank you again to our sponsors, Centene, Subaru, Missouri American Water, the City of St. Louis, Metro Lighting, MSD Project Clear, Solid Waste Management District, and Missouri Department of Natural Resources and Great Rivers Greenway. Without their generous support, we could not have put together this Earth Day half birthday week of action. Thanks again, Zeke, and we'll see you all later.